Hi, welcome to the second lab. In this lab, I would like to look at the memory mountain exercise together with you. So let's start it. The first thing we need to do is to connect to Beskov, and to do that, we need first to get a ticket in Kerberos. So to get the ticket on Kerberos, we do k init minus forwardable, and then our username of the PDC. So this is not KTH username, but is the PDC username. Then here we are asked the password, and here we put the PDC password. At this point, we are ready to go. We get a ticket, and so we can SSH Besco. SSH. Our username, so in my case it is Marquis, at besco.pdc.kth.ac. At this point we are on the login node of the Besco supercomputer. The first thing I typically do is to change the directory, because when we log in we are on AFS here, and as I told you in the previous lab, if we want to run something computing node, it needs to be on the CFS file system. The reason that the computing nodes are only connected to CFS file system and not to AFS. Sorry. So let's change the directory first. So is CFS klemming scratch the first letter of the username. So in my case is Marquis. So we are in CFS. What we need to do now is to get the code from GitHub. So what I do is git clone this copy, right? So we copy in a directory called memory mountain example. We change directory, memory mountain example. Then, according to instruction, we are supposed to change one of the file when running on Besco. So the file is here mountain.c. So let's do it. Emacs mountain.ec. Right, and we need to do is to change this max byte, that is the maximum size of the array that we are using in the memory mountain exercise. So instead of 27, we use 29. This is a left shift operator that basically is a nice and fancy way to express power of 2. So we take 1 in binary, and then we shift it by 29 position. On the left, that means also that we are basically increasing to the some power of 2. So we have done this fix. We are ready to go. Compile it. So I save it, and then so in order to compile, I use the. We need to do one first thing. So we are asked to use the GCC compiler, right? So by default, remember that when we log in, we are we have a set of a module that have been loaded. So module list is to see our configuration by default, and you see that we are basically using Craig compilers. So what we want to do is to do this module swap program environment create to program environment new, since we want to use the new GCC compiler. So we do that. So now if you do module list, you see that we have the new compiler, and the gray compiler environment disappear. To compile it, we just do make, because there is a make file here. You see, it's basically compiling mountain C and these other two files for the measurement. Okay, so let's compile it. Make. At this point, we have the mountain.out, that is our binary. So we want to run it. So remember that we are now on the login node. So we cannot really run something like this, because this is the node that is being shared by all the users. So if we want to use this, if we want to run it, we need to do a few things. First, we need to get an interactive section using Slarm. And the way to do that is using salloc, right? So let's see here, salloc. We go. I never remember how to do exactly. So here, compiling and running, right? So here we do salloc, right? So is so one node, 1 hour is probably too much. So let's change to 10 minutes, right? And then there is a -a and the name of the our allocation. So edu 20.ddd2356 -c, capital C as well. So we are remember that Besco has two kinds of nodes, some with the Haswell and some with the Broadwell. Since the memory hierarchy strongly depends on architecture, just make sure that we are selecting the Haswell nodes, right? Because we want to investigate the Haswell memory mountain. So I'm asking now some allocation. We are now on the computing node because our allocation has been granted. So now we do, in order to run, remember to do srun before the name of the executable. -1, that means just is serial, so just one process. And then it's called memory, mountain dot out, right? Let's see, this is it's kind of slow. Yeah, so it provides a matrices, right? So we want to have the results output to a file. So what we can do is actually to do this. We pipeline to results .txt, and so now it's actually running, but instead of displaying like we did before, is basically writing to this file results.txt. Okay, now we got the results for the memory mountain. What we like to do now is actually to copy these results.txt, copy to our local computer, and use new plot to visualize the memory mountain. So let's do exit for exiting the our interactive section using Slurm. So you see that we are releasing the resources, so we leave the computing node to somebody else, and then we do log out from Besco. At this point, I'm back to my laptop, and what I want to do is actually to copy the results .txt locally. So to copy from the supercomputer, I use the SCP, so it's like a copy, but with the S before SCP. Username, Besco, and then here at the end we need a semicolon. And then let's put the copy, the file is on CFS, and the text file is called txt, And then I want in this local directory, so I put a dot. Okay, we copied. So at this point, we can use, let's go back to the assignment. So I have in this directory this plot g, gplt. So I have a new plot installed on my Mac. And I also copy from GitHub this plot gplt in this downloads folder. Right, so there is some warning due to the fact that it's not getting the fonts. Let's see just very briefly how this confirmed, right? So you set the terminal to a PNG size, so the output is actually a file called memorymountain.png, and then there are some labeling. So let's go to the directory, and so this is the file that we just creating, right? So right, so this is the final results of the memory mountain. So on the z-axis we have the throughput, that is the in this case is the read bandwidth. So the higher it is, the better it is, right? So and then on this axis, y-axis, we have the size of the array, and the y-axis we have the stride the array is actually accessed. So this part of the memory mountain is for data that is rather small, that fit in the L1 cache. So here you see that the bandwidth for a small size array is very high, so is the top. The reason for that is also it fits it into the cache. So increasing the size of the array, you see that we are not able to use L1, L2, and 3, but we go here is probably the size of the main memory on the computing node. In order to access also a special locality, we can see what is the effect of the stride. And you see that spatial locality is lost for largest stride. So this was the first exercise, right? I would like to go now and just check the granularity test. So let me close this one. I'm back on my local laptop. There is a file I want to copy, right? So I think it's called clock granularity. That is the code to check the granularity of the timer that we are using. So this is the file I want to copy, and then I want to copy here, right? Yeah. So now I copy this clock granularity.c in AFS. Let's go back to Besco, right? So I still have the ticket, so I can do it. And then what I can do is cp. Our file is clock granularity, and then I copy on CFS, lemming, scratch, okay, this, right, and then we do this, right. So this point, what we can do is the compiler. So here we can use the create compiler, that is our compiler by default. And so let's see. So we can do scc and then clock granularity, right? So at this point, by default, we should have our executable, that is a.out. So we want to calculate the granularity of our timer on the computing node. So But at the moment, we are still on the login node. So what we need to do is to first to ask for an interactive section, right? And interactive section is the usual. So we use a slloc command, right? And one node, and then let's check, just 5 minutes, and we get so as well. So that's so now I'm in a computing node, and we can run srun minus n1. So if I omit minus n1, by default it's going to be 1, but just to be sure, we just put minus n1 out, right? So the code basically is sampling different measurement, and we need to put from the command line how many measurement we want to use. For the clock granularity, so we can do 500. Then what the assignment is suggesting is 100. So we do just 5 times more, right? So let's go back at the beginning of this output, and they gave us the clock granularity. Yeah, so this is the clock granularity of the timer that we have. So we have 3 numbers. So this is the minimum distance between different ticks. So this first number here is our clock tick or timer granularity. So that's the number we need to get for our assignment. Also, we have the maximum distance, right? That tells us basically what is what is the largest. This gives an idea more on performance variability and any interference of other tasks on the node. So you see that is so it's basically almost 1 factor as lower, right? So it might be something happens on the compute node that it might be delayed by a factor of 1 to the minus 6. So this is the value that we care about, right? So you see that is 9, so it's 10. So the timer that we are using is in the range of the microseconds, right? So we saw that many of the operations related to memories, if our caches are around between 3-10 nanoseconds, L2 might be between 50 nanoseconds. So clearly, this timer cannot do a very good job to do some measurement. It's very precise measurement. So what we also ask you to do in assignment is to look at different way to develop timers. In particular, we ask you to use one of the register of the Intel processor called RDTSC, that is the timestamp counter TSC, and is basically is a register that is having giving us a value of the elapsed time according to reset time. Expressed in clock cycle, right? So if you want to express in second, like in this case is expressed in second, you need to divide the clock cycle by the frequency of the processor that you've been using, right? So you will see that the frequency of the processor are typically in the range of gigahertz. That is 10 to the 9, right? So if that goes to the denominator, then it's 10 to the minus 9. That is a nanosecond, right? So it's much more precise timer. So let's look now at exercise about perf. So I just log out and copy one of the file that I want to use for using perf, right? So what I want to do is to copy um, one of the code that we want to profile is called matrix multiply, that is doing matrix multiplication, and then let's do this. SCP matrix multiply. Let's see. So to okay, so then we do we log in back to Basco, and then we copy matrix multiply to CFS. Okay, scratch. Good, and then we change directory to this one. Let's look at matrix multiply, in particular what is the size of the matrices. So let's size is quite small, is 100. Let's try to increase to 1000. Seems oh, so Basco start getting slow. Okay, good. So at this point we just we need to compile. So in order to do perf, we need the version. We need a binary, right? So then the perf will monitor, will profile the binary. So we compile it. So here is CC. So let's see matrix multiply, right? We might want to use one optimization flag to matrix multiply. So now is we have our binary that is by default, since we didn't put any an executable name, is aid.out. And then we want to do performance monitoring. Sorry, the monitoring of the cassette uses. Perf is an API that is an interface that allows us to check some hardware counter to see the performance counter that are available on Vasco. We do perf minus list. So it's not minus list. Oh yes, so it's perf list. Right. Okay, so this is some of the counters that are so for instance, we might want to use this L1 misses and loads, right? So what we can do then is so let's try to check L1 loads and misses. So this is Q, and so we want to run this on the compute node. So we need to do let's see if there's an SLOC here. We ask for interactive section using Slurm, one node, 5 minutes, using allocation either 20. And when we ask as well nodes, we're waiting now for an interactive section. Let's see how much it takes. In the meanwhile, we can just check the next step. So I'm looking at how to use a perf tool, right? So So what we can do now is to use perf stat minus EU, and then we are going to use these two counters. All right. It seems that is takes some time. Let's wait. Let's say it takes. Oh, now we got it. So now we are ready to run uh, um, our matrix multiply monitored by the perf counters. So we are in the compute node. So you know so we get first a list of perf list. Perf, always do this mistake. Perf list, and so we want to do we want to do this. Okay. Just recorded the name of the counters. So you do here, and let's put here. So we want to run on the compute node. So it's srun. Don't forget srun minus n. And then perf stat minus e, and then the name of the counters. So the first one is this one, right? And then the second one is this one. Let's see if we did correctly. Is perf stat minus e, and then now we need the name of the binary that is our matrix multiply by 1000. So let's try to do this. Okay, so it seems it's running. (1001) by 1000 looks small, but reality is quite big, right? So it does the multiplication, the time, right? And then you have to basically the two counters, measurement from the two counters. So these are absolute number, so that's the total number of load misses, and this is the total number of cache loads. So it's also nice enough to give you to give us the percentage of cache hits, right, and give the time. So so we can use perf to do to monitor many other counters. So the example we have in here, for instance, is just checking the. Yeah, so we cannot run like this. If we do that, we're going to run on the login node. So we do srun minus 1 to go to the compute node and do the perf there. Will take roughly 15 seconds right now. And we provide information about the CPU usage and the number of page faults. Here we go. So we can use perf as a tool to assess different performance counters available on the hardware. So this is everything for this second lab. In the next lab, we are going to look at other exercise. Thank you, and talk to you soon.